Hey guys, in this video I'm gonna teach you about what are emitter feedback bias circuits. So basically they are base bias circuits, but there's a slight difference, which is we put an emitter resistor also. So why we put emitter resistor? It is for basically the stability, right? So the gain formula is what? It is AV my negative RC over R dash E plus RE. So what happens is uh, R dash E basically depends upon uh, the temperature. So if we have a large RE value or resistor, so the change in temperature is much less because RE is much greater than R dash E. So the denominator will be not affected by small changes because it has a larger value. So the gain will be much stable. So this is about emitter feedback bias circuits. Now we can solve the circuit for the base voltage, emitter voltage and the collector voltage. So if you think of the base voltage, how would you find base voltage? You'll see the supply of 12 volts, a DC supply or the DC battery, which is connected to RB base resistor. So we will like look from here to the bottom, which is the ground. So we're gonna look what are the drops. So here's VCC. We'll call this drop as VRB. Let's say this drop is VRB. So we have VCC minus the drop across RB. Then we have a drop here. If we go from here, it's around zero point 0.7, which is we will call for timing VBE. So we write it a drop VBE, and there is also a drop across this emitter resistor. We will call it VE. So our expressions now look like this. We also know that from NPN transistor that the emitter current is the summation of base current and the collector current. Basically how transistor works, like if you a small change in base current produces a large change in collector to emitter voltage, right? So the base current is the summation of collector current and the emitter current, right? Also we know that a small change in base current will produce a large change in collector current. How much large? It is actually a gain factor, right? Beta. So the collector current is beta times IB. So we will put collector current value, which is beta times IB, into this equation. We'll get IB plus beta IB, right? Now we'll factor IB from this expression. We'll get beta plus 1 times IB. Now we'll put that IE equation into that equation. We'll get something like this, and if we solve for IB, we'll get an equation like this. Now we'll plug all our values from the circuit. VCC was 12 volts, there was a drop 0.7, RB was 110k, and beta was given as 200, and RE was 200 ohm. So we'll get a base current of 0.075 milliamps. Also, we know that IC is beta times IB as we discussed previously. So IC is gonna be 200 times the base current, which will give us 15 milliamps. IE, as we discussed, is the summation of base current and the collector current. So we'll add these two current, we'll get IE. From basic Ohm's law, we know that the voltage drop across the resistor is IA, the current across the resistor. The current across the resistor and the resistance value, this is the voltage drop, right? So we know the emitter current and the resistor we are supposed to find out. We can calculate the emitter voltage, right? So it turns out to be 3.01 volts. Also, we know that from transistor characteristics that, let's say this is base and this is the base voltage and this is emitter and this is the emitter voltage, and the drop is around zero point 0.7, right? So the base is zero point 0.7 higher than the emitter voltage, so we can say that the base is 0.7 higher than the emitter voltage. Now if we look back to our circuit, the collector voltage is, what is the collector voltage? If you look there, there's the DC supply, which is, there is 12 volt, right? So we need to find the collector voltage. We can just read, uh, we can just eliminate the drop. So 12 minus the current flowing through the resistor RC, that is IC and RC, will get to this point. So 12 volts minus the voltage drop across the collector resistor will get the collector voltage. Similarly, if we know the collector voltage and we have calculated the emitter voltage, so we can find the drop across the collector and the emitter. So it is around 5.9 volts. If we observe that if the temperature increases, this is the physical characteristic, if temperature increases, the beta increases, right? Because beta depends on internal resistances and internal resistances depends on temperature. Also, if you observe, if we increase the collector current, right, the collector voltage decreases. Why it happens so? If you look at this equation that we have just figured it out, so if you increase the collector current, because it is a negative term, so if you increase the collector current, this term will increase and this will affect the collector voltage to drop. So it if you say, you can say like they both have inverse relation. If one increases, the other decreases. So the collector current increases, so the the collector voltage decreases and emitter voltage increases. Why? Is like, we know that IE is equals to the summation of the base current and the collector current. Uh, so if IC increases, IC increases, emitter current increases, and if an emitter current increases, the emitter voltage increases. So this is why emitter voltage increases and the base voltage also increases. So this is all we have learned about what emitter feedback bias circuit. It is mainly used to stabilize the cue point in order to stabilize the gain. So hope you enjoyed this lecture. Catch you guys in next video. See ya.